Hello, welcome back. Today we're going to cover the concept of the exponential function in math. It has applications in algebra, in trigonometry, in pre-calculus, calculus, all branches of advanced math, and so on. And it's not every day that I have the opportunity to explain to you one of the most important functions in all of math, all of science, and all of engineering. So I'm very excited to teach this lesson here on the exponential function. At the end of this lesson, you should understand what an exponential function is, have some idea of its importance, although you'll continue learning its importance as we go on throughout your education in math and in physics and chemistry and other areas. And also be able to understand intuitively what the graph of the exponential function looks like. And I have a computer demo that we're going to integrate into this lesson as well, so you can see interactively what's really going on with this function. I cannot overstate how important the exponential function is in math. It's really, honestly, one of the most important functions ever, right? Let me give you a little motivation why. It's a crucially important function for lots of reasons, but just off the top of my head, if you like to make money and you like to invest money in the stock market, or you like to put money in a savings account and have it grow in the bank, the interest that you earn on money ends up following an exponential curve. So we're going to learn a lot after we understand what an exponential function is. We're going to study the growth of money, and that it follows an exponential curve. So if you like making money, exponential functions will do that for you. Also, when you take a loan out and you owe money in form of a debt, the debt grows monthly as well, and the growth of that debt is also an exponential function. So if you want to stay and keep your money and not have as much debt, exponential functions really are important for you to understand. And going back more to the pure sciences, when you have a bacteria that is multiplying in a human body or in a laboratory, it's following a growth, what we call exponential growth. So the population of the bacteria is not growing linearly, it's growing exponentially, right? Also cancer, when cancer grows in your body, same kind of thing, is growing exponentially. Also populations, population of Australia, population of UK, population of the world, population of some city somewhere. When you have generation after generation, producing offspring, the population follows an exponential curve like this. So it has practicality there. Getting more back into the sciences, we have radioactivity, right? When you have uranium and it decays into some daughter product, you might have heard the concept of half-life. When half of the thing decays into something else, that also follows an exponential type of decay. And here's the granddaddy of them all. You will learn later in your math and physics and classes down the road, engineering classes, that all waves, sine waves, which we haven't even talked about sine waves yet, but these up and down wave motions, right? They can always be written in terms of exponential functions. So that means literally every wave that propagates, radio waves, microwaves, X-rays, gamma rays, also all of the waves that we use in quantum mechanics to predict how matter is going to behave, those are all waves too. And all of those waves can always be written as exponentials. All waves can be written as exponentials. So this exponential function that we're learning literally has applications every branch of math and science and engineering. So that's why it is so incredibly important. Now what I want to do is get it on the board to show you what it is. Then we're going to do the computer demo to give you an idea of what the graph looks like. But then the rest of this lesson, we are going to dissect this function so that you understand exactly why the curve of this thing looks the way that it does. And there's a couple little kind of curves along the way. We'll be taking left turns and right turns to make sure you understand every little part of it. But ultimately, when you get to the end, I want you to know what this function is, what it looks like, and why it behaves the way it does. So what is an exponential function? Let me just give a couple of quick examples of exponential functions. And I'm just going to write these down in no particular order. If you have a function f of x equal to 2 to the power of x, notice that the x variable, this is different than x squared. We've been doing polynomials. F of x is x squared. That's a parabola. But in that case, the x is down low, and the exponent in x squared, the exponent is a number, just the number 2. In this case, the exponent is not just a single number. The exponent is the variable. So when you see the variable up in the exponent like that, that's an exponential function, right? Another example, f of x is equal to 10 to the power of x. This is a different exponential function than this one, but it is still an exponential function. F of x equals, instead of a number like 2 or 10, we can have fractions as well. We can have 1/2 to the power of x. right? So I have 3 examples here, and I could keep going on. I could say, 1/6 to the power of x, 1/10 to the power of x, whatever. But notice that they're all positive numbers down here at the bottom, and the exponent in every one of these cases is up in the variable. The variable is the exponent. So what we can say about this exponential function is the number down in the bottom is what we call the base. So this base, in this case, is equal to 2. The base is equal to 2 in this case. In this case, you might guess that the base is equal to 10. And in this case, you might guess that the base is equal to 1/2. So you can see that the base can be, the base has to be positive. And I'm going to write all of these rules down in a minute. It has to be positive, and it has to be, well, I'm just going to leave it at that. It has to be positive. You want to stay away from 0 being a base, and you want to stay away from the number 1 being the base. And I'll tell you why, as we get a little farther in, why 0 and 1 cause problems for this function. But any other number than that that's positive will give you an exponential curve, just with different bases, all right? So what I want to do now is go off to the computer before we get too far into this and just show you in general what this thing looks like. And then once we finish that, we'll come back and we'll draw lots and lots of pictures so you'll understand exactly what this function looks like and how it's calculated. Okay, welcome back. Here we have our computer demo. This is what we call an exponential function. This b right here is what we called the base. So let's first take a look at when the base is bigger than 1, like 2 to the power of x, or 3 to the power of x, or 10 to the power of x, or 100 to the power of x, and so on. So what happens as I increase this guy? You see what happens as the base, here the base is 1.6, and then we have the power of x. As the base gets bigger and bigger and bigger, this curve starts out very, very close to 0. It rapidly ramps up like a kind of like a rocket launch, and it kind of starts going up much more and more vertical. And as the base gets bigger and bigger and bigger, all that happens is the steepness of this part on the right-hand side gets more and more and more vertical. So if I crank this thing up all the way, I think the maximum I have this thing set was to 20. But if I go to 100 or 300, all that's going to happen is it's going to ramp up more and more and more vertically. Right? So you might think of this curve representing the population growth of bacteria. Starts off really, really, really small, but then as it builds momentum and each generation starts generating, daughters and little daughter bacteria and little son bacteria, and they continue to reproduce, then whammo, the thing goes straight up vertical like this. 20 to the power of x is a very steep exponential curve. As I back this thing down, you can see we start to bend the thing down closer and closer and closer and closer. Notice what happens when we get down to around 1.5 to the power of x. We have a very gentle curve that goes up. One thing I want to point out to you, the most important thing, is that this exponential function, look at the scale of the y-axis. Here's 5 and here's 10. So the tick marks are 1, 2, 3, 4, 5. So this tick mark right where the curve crosses right here is actually at the y-intercept of 1. Notice what happens when I change this curve. No matter what it looks like, it always crosses the y-axis at the same spot. The curve to the left and the curve to the right changes shape, but it always goes through the same location. Why is that? Because if I take a value of x is equal to 0 and stick it in this to the equation, 4.9 to the 0 power is just 1. So that's why it crosses at 1. If I change this curve to 20 to the power of x, I put an x value of 0, 20 to the power of 0 is still 1. So it still crosses here. If I go way, way, way down here to 3.2 to the power of x, stick in a value of x is equal to 0, 3.2 to the 0 power is still 1. So no matter how I play with this curve, it always crosses there. Now notice when I get down all the way, I told you get into problems when you have 1 to the power of x. See, 1.1, you have a very gentle slope up. When you get down to 1 to the power of x, it just flattens out completely. And that's because 1 to the power of x, no matter what I put in for x, whether it's 1 to the power of 2 is 1, 1 to the power of 4 is 1, 1 to the power of -2 is still 1. No matter what I put in for the x value, when I say 1 to the power of anything, I always get 1. So basically this exponential function turns into a flat line when you put 1 as the base. And that's why I told you need to stay away from 1 being the base. And also the same thing, similar thing happens if you put 0 as a base. If you put 0 as a base, 0 to the anything power is still 0. So that's not an exponential function either. So you cannot have a base of 0 and you cannot have a base of 1. But any positive value, notice everything bigger than 1 just yields a steeper and steeper curve. Now let's go down and take a look at what happens when the base is not 0 over here, and it's not 1, but we just constrain it to be between 0 and 1, because the curve up here only looked at what happens when the base is bigger than 1. Of course, it gets steeper and steeper. But down here, we're just saying, what happens when the base is 1/2? What happens when the base is 3/4? What happens when the base is 1/10? Things like that. So what I can do is crank this thing this way, and you can see what starts to happen is the exponential function starts to look like the exact mirror image of what's above. Look at this guy here at 0.2 to the power of x, and then I can crank this guy up so that it looks something like a mirror image. I mean, I can adjust everything to make it exactly the same. I'm not interested in making it look the same, but you can see that the shape of the curve looks the same as it does in the previous case. It's just that for the negative values of x, that's where the curve starts to go into the stratosphere, and then it just goes down to 0 as we go on to the positive x direction. We're going to get into exactly why it does this in a minute. So here we have the positive values of x. It gets steeper and steeper, still goes through the value, the y-intercept of 1. Here, if we have the base be a fraction like 1/2 or 1/3 or whatever to the power of x, we have the same shape, but it's just a mirror image on the other side. Again, it goes through the y-intercept of 1. Anything to the 1 to the anything, any base to the power of 0 is just going to give you a 1. So it goes through the same spot here. Now what we're going to do is combine those two things together. We're going to say the base is going to be bigger than 0, but can also be a fraction as well. So when we go larger and larger values of the base, we have that nice skateboard type shape to the right. When we back it down here where we have 1 to the power of x, we get to where it's flat. And then when I go just on the other side of 1, then you can see this thing curving up the other direction. So you see the nice symmetry here. What's going on when the base is a fraction is you can make it steeper and shallow over here. And then when you go through 1, it gets flat, exactly flat. And when you go through 1, you have that nice shape happening on the other side. So this is what the exponential function does. Notice it always crosses through the y-intercept of 1. Okay, like this. And that is all I'm going to show you right now. I do want to show you what happens when the base gets less than 0, but I'm not going to do that until the end of the lesson because I think it's going to make a lot more sense then. For now, what I want you to realize is when the base is bigger than 1, you have this very steep curve in the positive part of the x values. When the base is a fraction, like 1/2 or 1/3 or whatever, you have the steep part of the curve on the negative x side. And when you put those two things together, you can just see it how it behaves, going through a flat curve, a flat line, and being exponential on both sides of this guy. So what I want to do now is stop the computer demo, go back to the board, and really understand why this function behaves the way that it does. All right, welcome back. I hope you've enjoyed the computer demo to really get an intuitive feel for what these exponential functions really look like. Now, what we learned from the computer plotting that we did was that the exact shape of the exponential function really is going to depend upon the base. The number that we have down in the bottom below the exponent is going to determine the exact shape of the curve. However, the general shape of the thing, as far as it sloping upward like that, generally looks the same among all of those, but the exact steepness of it, of course, depends on the base. So just a couple of rules I want to make sure and get down here on the board to make sure they're not lost. So I'll just kind of put this under some miscellaneous note, right? The base must be positive. Notice that when we did the computer demo, we did fractions like 1/2, 1/3. We did fractions all the way just above 0, all the way to 20, to positive 20. So any positive number is okay, except there's a couple of gotchas that you have to be careful about. Base must be positive. However, the base must not equal 1. Why? Because if I put a base of 1 here, 1 to the power of x, no matter what I pick for x, 1 to the power of anything If x is 1, if x is 2, if x is -1, 1 to the power of anything is just 1. So we saw that when the base was 1 in the computer demo, it was just a flat line. That's not really considered exponential. In order to be an exponential curve, it needs to slope upward one direction or another. So the base cannot be 1. If you put a 1 in there, it's just not going to really be an exponential curve anymore. Also, the base must not equal 0 for similar reasons. If I put a 0 in here, 0 to the power of anything is just going to give me 0. So if you put a number 1 in for the base, you're not going to get an exponential function. If you put a 0 in for the base, you're still not going to get an exponential function. Any other positive number is going to give you an exponential function with varying shapes. Now, you might probably be wondering, what happens if the base is negative? What if I put a -2 for the base? What if I put a -10 for the base? I'm going to save that for the end of this lesson. I would like you to know what happens, but I don't want to talk about it now because it doesn't give you an exponential function either. For now, just know that the base has to be positive, but it can't be 1 and it cannot be 0. All right? Now, some of you might be looking at this and saying, well, we've kind of studied functions similar to this in the past. We've studied things like, for instance, f of x is equal to x squared. This kind of has an exponent there. We've studied f of x, x cubed, x to the 4th, but this is different. This is f of x is something like, whatever. I could pick the base that I want, 6 to the power of x. You see, I really want you to understand the difference here. These things are just polynomials. They are not exponential. These are not exponential. But this one is exponential. It's an exponential function. So the only thing you have to look for is if the variable is in the exponent, not a solid number here, but the variable itself is up top in the exponent, then you have an exponential function. Then the exact shape of the curve is going to be governed by the base, right? So we have to split it up into two pieces. First, like we did in the computer demo, I want to talk to you in more detail what happens when the base is bigger than the number 1. Right? And then we're going to talk about what happens when the base is a fraction somewhere between 0 and 1, because we saw in the computer demo it flipped everything around and made the curve kind of mirror image, and that we need to explore a lot more in a lot more detail. But for right now, let's go and talk about something very, very important. Let's take a look at an example, one of these. F of x is equal to 2 to the power of x. That's an exponential function with the base of 2. And what I want to do is just spend a minute trying to draw a pretty good graph of this. Now, is this graph going to be as good as a computer? No, that's actually why I showed you the computer first. It's not going to be as good, but we can still learn a lot. Why does it start out low, and why does it get steep like this? And why does the steepness change depending on what the base is? I want to get very, very, very comfortable with that. Now, we saw in the computer demo that when x is equal to 0, all of these curves cross at an intercept point of 1. I'm going to put the number 1 up above here. Okay? So we saw that when the base was a positive number bigger than 1 like this, it starts way over here close to 0. I'm probably going to mess this curve up, but it goes really, really gently, slowly increasing right through this point and then kind of going up something like this. Is that perfect? No. It's a little bit lumpy. It should be nice and smooth. Now, the exact shape of it, of course, depends on the base. As the base gets bigger, 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 this thing gets steeper, steeper, steeper. As the base gets smaller, 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 it lays more flat till eventually it's just a flat line, and then it flips over and goes the other direction. We saw that in the computer. But why is the thing curved this way? Because when you take and put in an x value of 0 into this thing, what do you get? I'm going to do a lot of little substitutions down here below. You get 2 to the power of 0. But 2 to the power of 0 is just 1. So you see the number 1, it crosses at the y value of 1. Now let's go and put a few values in there. 1, 2, 3, 4, 5, -1, -2, -3, -4, and -5. So this is -5, -4, -3, -2, -1, 1, 2, 3, 4, and 5. And what I'd like to do is just spend a second to understand how this thing increases. If we put the value of 1 in here, then what we're going to get is 2 to the power of 1. That just means 2, because that's all it is, 2 to the power of 1. So we get a value of 2. So I'm not going to plot it. This graph, this y-axis I have is not exactly right. My curve is not exactly right. But you can still see that as I go up here, when I put a 2 in there, it'll be 2 to the power of 2. This goes into the exponent location, which gives you a 4. right? And then you can see that as I put 3 in there, it's 2 to the power of 3. 2 times 2 times 2. This gives you an 8. So you see what's happening is it's increasing faster and faster. When I put a value of 4 in, 2 to the power of 4, I'm going to get 16. 2 times 2 times 2 times 2, 16. And then when I put a value of 5 in, I'll get 2 to the 5, and I'm going to get 32. So you can see these numbers, 2, 4, 8, 16, 32, it's doubling every time. And that's kind of the genesis of the exponential growth part. When you put money in the bank and it earns interest, we're going to study it more later. But you have an exponential effect because when you earn money one year, that money is still in the bank for the following year to help earn more money. So the more money you earn, the more interest you earn the following year because the money you earned in year 1 starts to earn more money in year 2. But then in year 2, you have even more money, which then generates more money. And so it goes up and up and up in an exponential fashion. So that's why the curve gets so steep so quickly. Look at how fast these numbers are increasing. Now, when we go to the other side here, let's switch colors for this. When we go to the negative 1, a lot of students don't really quite understand why this works the way it does. If you put a negative 1 in for the exponent, it'll be 2 to the power of negative 1. But this is just the same thing as 1 over 2 to the first power, which is the same thing as 1/2. Okay, so we have 1/2 here. And that's why it gets smaller than 1. Notice it gets smaller than 1. Now, we have a similar thing right here. If we put 2 and put this exponent of negative 2 here, then this becomes 1 over 2 squared, which becomes 1 over 4. So it gets even smaller. And you can see the pattern here. This, I'm not going to substitute every little thing. This is going to be 1/8. This guy is going to be 1/16. And this guy is going to be 1 over 32. So you see, the numbers that you have on the positive side just become 1 over those numbers on the negative side. So as fast as this thing is increasing this direction, it is chopping it down just that fast going the other direction. This is why the shape of the curve for the exponential function, in this case we just pick 2 to the power of x, starts out very small because 1 over 32 is a really small number. But as we get, it builds very, very, very slowly. And it always goes through the point 1, but then it just rockets up because when you get into positive territory, everything starts stacking as we just described here. And that's called exponential growth. Okay? If we change the base, we're still going to be going through this crossing point of y is equal to 1. That's really, really important for you to know. In fact, I do want to take just a second before we talk about the negative side just to kind of draw some comparisons, right? So you might say, well, we've studied functions like this before, and we just talked about the fact that these are not exponential functions, but a curve that looks kind of like this is the x square curve. I'm not going to clutter up this curve, but you remember the x square parabola goes down and then up, so it kind of has an upward slope like this. But one thing that's not, I think, made clear enough in most books is that an exponential function like this, if you give it enough time, if you go out far enough, will always go up steeper than a polynomial of a similar degree, right? So in other words, if I were to plot x squared, what's going to happen is if you square this guy, you're going to get 1. If you square this guy, you're going to get 4. If you square this guy, you're going to get 3 times 3 is 9. So you see the x squared function is actually beating this function here because 9, for x squared, if I did 3 squared being 9, is bigger than this guy. 4 squared is 16. So right at this point, the x squared function is going to kind of intersect here, and it's going to start to not win anymore, because if you square this guy, 5 squared, you're going to get 25. That's not as big as 32. So what happens is the parabola function, x squared, which is kind of similar because the base is 2 and x squared has a 2 in the exponent. It's going to actually beat this function in the beginning, but then eventually, if you give it enough time, the exponential function will always overtake a polynomial and rocket higher. So that's why if you ever want to, earn money or interest or study bacteria or anything that has an exponential kind of growth, that's why it gets out of control so fast, especially in terms of debt, when you can owe so much money so fast, because it just builds on each other, on itself year after year after year, and it kind of just rockets up and starts to go vertical like that. Okay? One more thing I want to bring very importantly home is that 0, 1 is, or I should say lies, on all exponential functions. I've said this several times, but it's important enough to make sure you understand. What I mean by this is the y-intercept is 1, right? If I take, for instance, f of x, let's take a crazy exponential function. Let's say it's 100 to the power of x. That's an enormously steep exponential function, right? But if I put a value of x is equal to 0 in here, I'm going to get 100 to the power of 0, which is just equal to 1. So this means that the point 0, 1 is on this curve. So just like we saw in the computer demo, even if I crank the base up to 100, all that's going to happen is this is going to get very, very steep, but it's still going to come down through this point, and then it's going to get really, really small on this side. Okay? Now, so far, we've talked about positive values of the base. I want to draw a few more pictures about the positive values of the base, and then we're going to move on and talk about what happens. I should say, we've talked about positive bases that are bigger than the number 1. Base is equal to 2, base is equal to 3, base is equal to 4. In just a second, we're going to talk about fractional bases where we see the exponential function flip over to the other side. Okay, but before I do that, right underneath this, I want to draw a few different cases, which we saw in the demo, but I want to draw a couple of cases to make sure you understand why this thing gets steeper and steeper and steeper as you increase the base. So let's take the case that we just have right here. F of x is equal to 2 to the power of x. And we're going to graph this guy right next door to a couple of alternatives just so we can kind of see what happens. So it's going to go through the value y is equal to 1. We know that. And it's going to start something like this and something like this. And we know we can just pick whatever number we want. Let's pick the number 3, just as a point of comparison. X is equal to 3. When we put a value, and of course my scale is not right at all here, but if I go up here and I go right here, what's going to happen whenever I do this is that this value right here, it's going to be 2 to the power of 3, which is 8. So my scale is not right, okay, because there's 1 here and there's an 8 here, but you get the idea. We're going to cross up and we're going to come up to a value of 8, okay? Now let's take another example, and let's say what happens if we increase the base to f of x is equal to 3 to the power of x. What will something like this look like? Well, we're going to have a curve that's going to go like this. It's going to be x and f of x like this. We know it's going to go through the number 1. Yes, I know that my scale is not perfect, so don't get too mad at me. But basically what I'm telling you is just what we saw in the computer program. It's going to start out very, very slow, and then it's going to go a little bit steeper. Why is it going to go a little bit steeper? Because again, if I take the same number 3 here and put it in here, it's going to be much, much higher. Why? Because this point is going to be 3 to the power of 3, and 3 to the power of 3 is 27. So the crossing point here is actually at 27. So that's why increasing the base makes the thing get steeper, because here we're just, as we go along in x, we're just going 2 times 2 times 2, however many times you're doing it. Here we're going 3 times 3 times 3, however many times we do it. So if we pick the same value of x, of course the curve is going to be steeper here. And we can make a similar argument on the other side. It's going to get closer to the x-axis on the other side as well. Okay, so as the base gets bigger and bigger, larger than 1, the exponential function gets steeper and steeper, but it always goes through the y-intercept of 1. Okay, now what we want to do is we want to take a look at what happens when this base, here in this case it's the number 2, when this base is allowed to be below the value of 1. Because remember, when the base is 1, it's exactly equal to 1, we don't have an exponential function at all. But when it's less than 1 but bigger than 0, we have something really interesting happen. We saw in the demo that this curve flips backwards and starts high on this side and gets very low on this side. So we want to describe exactly why that happens. So let's take a look at that. Let's take another exponential function. Let's say f of x is going to be equal to, instead of 2 to the power of x, let's take a look at 1/2 to the power of x. Same kind of thing, we're just going to draw a crude graph. It's not going to be exact at all, but we're going to do our best. All right, so let's do the same kind of numbers. 1, 2, 3, 4, 5. So 5, 4, 3, 2, 1, 0. Then -1, -2, -3, -4, -5. -4, -3, -2, -1. All right, what I'm claiming is that this function is going to go through the exact same point. It's still going to go through 1. It's still going to go through 1. But instead of being high on this side, it's going to be high on this side. So I'm probably not going to be able to draw this right. I apologize. Let me start this way and see if I can get it. Go like this, right through this point, like this. That's not actually too bad. You see, it's a mirror image of what we have over here. Why is it a mirror image? Let's take a look at it. If we take the number 0 and put it in there, we're going to have 1/2 to the power of 0. That equals 1. So we have to go through the point 1, just like always. This guy is going to be 1/2 to the power of 1. So you can see right away, this is going to give you a value of 1/2, so it has to be lower. And then this guy, I'm running out of space here, it's going to be 1/2 to the power of 2, which is going to be 1/4. So it's going to be 1/4, so it's going to get smaller and smaller. And then this guy, you can see it's going to be 1/2 to the 3rd power. So 2 times 2 times 2 is 1/8. Whoops, 1/8. So it's going to get smaller. And then over here, you're going to have 1/16. And then over here, you're going to have 1/32. Okay, now let's go the other direction. We'll pick another color for this and go this way. Now take a look at what happens right here. Right here, we have 1/2 to the -1 power. To the -1 power means it's the same thing as 1/1/2 to the 1 power. But I can flip this thing over, and that means this value is going to give me a 2. So this side actually pops up higher than the 1. Okay, here it's going to be 1/2 to the power of -2, and it's going to be the same kind of thing, 1/1/2 squared. So this is going to be 1/4, and when you flip this guy over, when you do the division, 1 divided by means you flip it over, you're going to get a 4. Same thing is going to happen here, except you're going to get an 8. And right here, you're going to get a 16. And right here, you're going to get that 32. So you see the numbers, the 32, 16, 8, 4, 2 are the same numbers on the bottom here, which are the exact same numbers we got here. So it literally is the mirror image. Here, the positive values of x gave me large values, and here they are. Over here, when the base is 1 over the base we had there, the numbers are the same. It's just that the larger side is on the left and the fractional side is on the right. So it literally is like taking that function and reflecting it to the other side like this. It's an exact mirror image because this base is just 1 over this base. But of course, if I change this base so that it's different than 1/2, then I'm going to, of course, have a slightly different curve there. And as I play around with that base, making it closer to 0 or closer to the number 1, then I'm going to change and make it steeper or less steep. And I do want to take just a second to show you what that would look like. All right, so what I want to do is just do a little bit of a comparison to see how this curve changes as we change the base. We saw that in the computer demo also. So let's start out by coming over here and taking a look at what happens if we change. Well, let's go ahead and draw what we have actually. Let's say we have 1/2 to the power of x. This is what we just drew. I'm just going to kind of re-sketch it over here as a point of comparison, like this. We know this function is going to go through the number 1, 0, or 0, 1. And we know it's going to be pretty gradual in general. It's going to start out something like this. It's going to go through this point as close as I can get it, something like this. Now let's pick a point of comparison. Let's pick the point -3 out here, which is going to intersect something like this. What is this point going to look like? It's going to be, when we do 1/2 to the -3 power, right? It's 1/2 to the -3 power. We go over here and we see we're going to get an 8. How do we know that? 1/2 to the -3 power, it's going to be 1 over 1/2 cubed, so the thing gets really big, and what we're going to get is 8. We just saw that here, so we see that it's higher. Now let's do the exact same curve, but let's change it so that we say f of x is equal to, we change the base to make it even smaller, 1/10 to the power of x. Kind of draw a little dividing line right here. So I'm comparing this to what happens over here. What's going to happen whenever we make the base really tiny, close to 0? Well, we're going to show in just a second what's going to happen is this function is going to be really steep, but it's still going to go through this point, and it's going to get like this. You see how this one's a lot steeper? I may not have drawn it perfectly, but this one's supposed to be a lot steeper. Why is it going to be steeper? Because if I go to the same place, -3, what's this point going to look like? It's going to be 1/10 to the -3, which is 1 over 1/10 to the power of 3, which this is going to be 1 over 10 to the power of 3 is going to be 1,000. And then 1 over, or I should say, let's just do it like this. 1 over 1/1,000. And that's going to equal 1,000. You see, it's 1 over the fraction 1 over 1,000. You flip this guy over, you're going to get 1,000. So this value right here is actually way up here at 1,000. Now, of course, I didn't draw it right. This thing is actually much, much steeper. It should be going really, really low and getting really, really, really steep when you make the thing so small like this. So the bottom line is that as you start off with a base very, very close to 0, you have a really steep curve, really steep. As you make the base bigger and bigger and bigger, closer to 1, this bends down so that it's getting closer and closer. When you make the base equal to 1 exactly, you have a flat curve that's not even really an exponential function. But then, as you increase the base past 1, so you get to 2, it gets a little steeper, and then when you get even higher, it gets a little steeper. This behavior of starting high, getting flat, and then going up again is what we saw in the computer demo. And that's why. It's because when you have these negative values here for x, and you're putting them in here, then you have to do the fraction arithmetic to flip it upside down, and that's why it gets getting bigger on this one side here. That's extremely confusing when you first learn an exponential function. Why is it getting steeper when the base is a fraction on the opposite side of when it's getting steep when the base is bigger than 1, okay? So now that we have all of that background in place, we can finally write down what you'll probably see in your textbook. This is an exponential function. Exponential function. And in general, you know, we've already talked about this, but I want to put it all in one place. The exponential function is the following. It is a function, f of x is equal to some base to the power of x, right? With b greater than 0. The base has to be greater than 0, and b is not equal to 1. This is exactly what I told you in the beginning. I told you the base can't be 0 and the base can't be 1, but the base must be positive, okay? So that's all I'm saying is how you would typically see it in a book. It'll be exponential function with b to the power of x. B has to be greater than 0. That means b can't be 0, but it cannot be equal to 1. Any other number is fair game. And then you have different cases, right? And we've already written all this down, but I'm putting it all in one place. If b is greater than 0, but less than 1, this means it's a fraction somewhere between 0 and 1, then in general the exponential function is going to look something like this. It's going to go through the point 0, 1 on the left-hand side, right through this point, something like this. Okay? If b is exactly equal to 1, which you can't really have, but I'm just putting it here for completeness so you can see what it actually, in your mind, you can see what would happen, is the line is not an exponential function at all. It's just flat. So you can't really have, this is not an exponential function. I'm just putting it here to show you what would happen if it is equal to 1. And then finally, if b is greater than 1, what you get is that standard exponential function that we have already talked about, where it goes through 0, 1, starts off really, really small, goes through this point, and rapidly goes up high like this, bigger than 1. If you have a base of 1, it's not really an exponential function. If you have a base of 0, it's not an exponential function. So that's why those constraints are there. Now, the one point of curiosity that most people have is what happens if the base is negative? We said the base has to be bigger than 0. We understand 0 to the power of whatever is not going to be an exponential function, but we said it has to be bigger than 0, and it has to not be 1. That all makes total sense. What happens if we put a value, a negative value for the base, into this equation? The answer is it's not an exponential function, and I want to tell you just a second why it's not an exponential function. Let me go find some room, I think over here. Let's say the base is negative. Let's just pretend. You cannot have, this is not going to be an exponential function, but what's going to happen? Let's say f of x is equal to, let's just say, negative 2 to the power of x. I mean, at first glance, it looks like it would be an exponential function. But think about it for a second. What's going to happen if you put a value of 1 here? Let's just pretend. Let's say f of 1. Okay, that's going to be negative 2 to the first power. So f of 1 is going to be equal to -2. All right, so far so good. Let's say we go up to the next guy and say, let's put a value of x is equal to 2 in here. 2. And that means that we have -2 to the second power. Now you see, because negative times negative is positive, this is actually going to be a positive 4. All right, now let's do one more. What if we go up one more and say f of 3? It's going to be -2 to the 3 power. So f of 3 is going to be -2 times -2 times -2. So -2 times -2 is positive 4. Positive 4 times -2 is actually -8. You see what's going on here? As we put different values of x in for our regular exponential function, it's a very smooth increasing value that just goes up and up and up. But here, when the base is negative, you have this oscillation happening. Here, we just had, when we put a value of 1 in, we got a negative value out. But then we put a value of 2 in, and we got a positive value out. But then we put a value of 3 in, and we got another negative value out. So it's like, it's going positive, negative, positive, negative. So what's going to happen is it's going to get bigger, 2, 4, 8, 16, 32. But positive, negative, positive, negative, positive, negative, it's going to oscillate. And that is not an exponential function. So that's why when we say an exponential function is when a base is greater than 0, but it can't be equal to 1, the reason we're saying that is because you put negative bases in here, you can calculate the answers, but it's going to have this oscillation effect, up and down bouncing, and it's not going to be a smooth exponential function. So let's take just a second to go take a look at that in a computer just to satisfy your curiosity to see what that actually looks like. Hello, welcome back. So here what we're going to do is see what happens when the base is less than 0. Now first, let's remind ourselves what happens when we increase the base. This is a positive base, getting bigger, 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 bigger. We have this nice exponential function going really, really, really steep. As we get down here to where the base is now getting close to the number 1, it gets very flat. The scale is a little different here, so it gets very flat. And then when we get to fractions, we see that the exponential function gets larger on the other side, mirror image like we just described. Now this is 0.2 to the power of x. Let's still, oops, I gave the punchline away. Let's go and let it get to where we have a negative value in here for this base. It gets very, very high, and then if I can tweak it and get a negative value here, we have this oscillation kind of effect. You see how these oscillations are happening? We're bouncing positive, negative. It's still getting bigger. It's just the absolute value is getting positive, negative, positive, negative. And if we crank it up even more than that, we're going to see this thing go out of control, and then we're going to see an oscillation effect on the other side. So you see how we still have a mirror image kind of thing going on where it gets bigger on one side and bigger on the other side when the base is negative. But this oscillation effect that I just described on the board is what prevents this thing from becoming an exponential function. This is a perfectly valid function. It's just not an exponential function. So let's go ahead and wrap up the computer demo and go off and wrap up the lesson. All right, welcome back. I hope you understand now what an exponential function is and why it is so important. The bottom line is an exponential function is when we have a number raised to a power, raised to an x variable like this. The number on the bottom is what we call the base. The shape of the exponential curve depends on the base. We went through all of this kind of background information, ultimately arriving at something like this. We can see that when we put bigger and bigger values in for a positive base bigger than 1, it gets steeper and steeper. If we change the base, the curve still goes through 1, but just gets steeper. If we increase the base, we can actually see it getting steeper right here. Then, if we flip it around and say, well, what happens when the base is a fraction between 0 and 1? We have the exact mirror image. We have it getting steep on the left and getting very small on the right. The reason it does that is because of the way fractions work with powers. When we have negative powers applied to a fraction, it ends up becoming 1 over that fraction, which flips it over and makes it very steep. Similar reasons is why this becomes very shallow right here. But still, when we adjust this base, even if it's in between 0 and 1, we can change the shape of this exponential curve. As we make the base closer to 0, this is much smaller than that one. It gets much, 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 very, very, very steep. As we get it closer to closer and closer to the number 1, then of course it bends down, as we have seen it do in the computer demo. And then finally we have the exponential function. It's b to the power of x. The base has to be bigger than 0, but it cannot be equal to 1. If the base is a fraction between 0 and 1, you're going to, in general, have a sloping downward type of function that's big on the left and small on the right. If you have a base larger than 1, it's the exact opposite, small on the left, big on the right. Of course, the exact shape depends on the value of the base. If the base is exactly equal to 1, the function is not an exponential function anymore. It's completely flat. And we talked about why that's the case, and that's why you cannot have a base equal to 1. And we just saw in the computer demo, if you actually got crazy and put a negative value in for the base, then you have this kind of like oscillating beast that's not an exponential function at all. That's why the base can't be negative. So I hope you understand exponential functions. Burn these graphs into your mind. Please, because really and truly exponential functions is one of the most important functions in all of math. We are going to come back to it again and again and again. And when you get into calculus and other advanced subjects, it's going to become even more critical. So please make sure you understand this. Follow me on to the next lesson, and we're going to learn how to solve equations that contain exponential functions.